As always, so many things to do. All right. Hey, everyone. I'm
Hello.
Fraser Cain, and welcome to the weekly Space Hangout for Friday, March 27th, 2015. So, joining us this week, we've got a regular crew of space folks, but we've got a very special guest. So, I hope you enjoy. So, joining us this week, we've got Dr. Brian Koberlein. Hey, Brian.
Hi.
We've got Dave Dickinson from
Hey.
some snowy place.
Somewhere in Maine.
Some-
It is now astronomical spring officially, as of last Friday.
We've got Morgan Rehnberg. Hey, Morgan.
Hey, Fraser.
And as I mentioned, special guest. We've got Sukanya Chakrabarti from from literally just down the hall from Brian at the Rochester Institute of Technology. And Sukanya is going to be talking about the discovery of a dark matter galaxy. Welcome to the Weekly Space Hangout.
Thanks for having me.
All right, so I know your time is pretty tight, so we'll kind of focus on that first before we get to all the other stuff. But before we do, I just want to remind everyone that this is a live show. You can post any questions or comments that you want. Just go ahead and use the Q&A app to do that. You can go to, if you're watching this, click you're interacting with the audience, click that, post your question. We'll be glad to answer it. So. All right, so Sukanya, why don't you sort of give us a little bit of history here about sort of what you found?
Sure. Well, several years ago, when I was a postdoc at Berkeley, I analyzed disturbances in the outer gas disk of our galaxy. So you see large ripples in the outskirts in the gas disk of our galaxy that wouldn't be produced in a purely isolated context. So we asked the question, what would have caused these kind of ripples? And I did a set of computer simulations of the Milky Way interacting with dwarf galaxies, and I was able to calculate the mass of the dwarf galaxy that would be needed and how close it would have to get to produce the observed disturbances. So I made a very specific prediction, and the prediction was that the dwarf galaxy is about 1/100th the mass of our galaxy, and is currently about 300,000 light years away from the center of our galaxy, in the southern part of the sky. So I developed this method more over the last few years, and last year I was interested in trying to get observational confirmation for this dwarf satellite. Now this is difficult because the prediction was that it's very close to the plane of our galaxy, so you're looking through a lot of obscuring dust and gas. And so you really need a deep infrared survey. And we had that, we had data from the Visa variables of the Via Lactea. That survey was done by a group in Chile, and I analyzed data from that survey, and I found clustered Cepheid variables. These are young pulsating stars, and they're very important to astronomy because in the early 1900s, Henrietta Leavitt showed that if you measure the period of pulsation. So if you look at the magnitude of that star, it's varying periodically. And she showed that if you measure the period, you can infer the distance, because there's a period luminosity relation. So these Cepheids are center candles that we can use to figure out their distances quite accurately. And the really exciting thing was that these Cepheids that we found are the average distance is about 300,000 light years away from the galactic center. And the stellar disk ends much closer, so the fact that we see these things so far out and the fact that they're very highly clustered in distance and in angle suggests that they're part of a dwarf galaxy, a dark matter-dominated dwarf galaxy. So that was really exciting.
Right, and I think that's the punchline, is a dark matter dwarf galaxy. And I think this is something that a lot of astronomers have been theorizing for a long time, right? That there should be that the connection between the dark matter and the stars and the regular matter that we can see in them are there's some link going on there, but there's also situations where we can see perhaps the dark matter and the gas of the galaxy being stripped apart. So what kinds of conditions would create, I guess, a galaxy that seems to be largely dark matter?
So there are various conditions that can lead to that. In particular, in this context, we have a dwarf galaxy that's come very close to the Milky Way. Okay, so about in my simulations, the distance of closest approach is about 10 kiloparsec from the center of our galaxy, and then it moves away. So if it gets that close, it very likely will lose. Some of the material is going to be stripped off. So some of the luminous material, the gas and stars, could easily have been stripped off in a very close passage. And you see that. You see tidal debris from other known dwarf galaxies, like the Saggitarius dwarf galaxy, for example. The tidal debris is widely spread in the Sagittarius dwarf galaxy over the sky.
Right, so I'm kind of imagining the situation where you've got this dwarf galaxy, just like some of the others that maybe we're more comfortable with, the Large Magellanic Cloud, things like that. This dwarf comes close to the Milky Way. The gas and the halo around the Milky Way, I guess, that starts to collide with the gas and dust in this dwarf galaxy and sort of pulls it out, streams it into a tidal tail. But because, I guess, the dark matter itself doesn't have any kind of cross-section, it just is able to kind of pass through and just keep going. Is that sort of right?
Yeah, more or less. I mean, some of the dark matter is also going to be stripped off. And for example, and it depends largely on how the dark matter is distributed in the particular galaxy. In the Sagittarius dwarf, about 70% of the luminosity is in the tidal tails. So, a significant fraction of the stars can be stripped off when you have interactions between the Milky Way and the galaxy.
Do you think that there's a situation where you could get a galaxy that is just dark matter that didn't have some interaction that stripped out the gas and stars? Like, could you just have a clump of dark matter form in place and that just be the dwarf galaxy?
Well, I mean, in principle, yeah. So there are these new objects that have been discovered in the Alfalfa survey called ultra-compact H2 regions. And so these are gas clouds that have been found, and there's very little evidence of star formation. Now, if you do very deep optical surveys, you see a few stars, but it's effectively just a gas cloud that has, from looking at the velocities, additional material than just the gas and visible stars alone.
So based on what you have uncovered and the evidence that you've gathered so far, do you think that there are a bunch more of these surrounding the Milky Way?
Yeah, I mean, so we've been finding dwarf galaxies by the dozens over the last, in the astronomy community in general, we've been finding dwarf galaxies by the dozens over the last decade. So the Sloan Digital Sky Survey more than doubled the number of dwarf galaxies. Recently, the Dark Energy Survey has found evidence of potential new Milky Way satellites. I think, in the future, one of the important things to realize is that, even though Sloan has made great advances, the sky coverage for Sloan was incomplete. Okay? So, because it didn't go below a latitude of 30 degrees, because it's an optical survey, it's difficult for an optical survey to survey regions close to the galactic plane because of the large amount of dust acceleration. Now, many of the discrepancies that we now see between cosmological simulations and observations, I mean, like the missing satellites problem, for one, the prediction from cosmological simulations is that there should be thousands of dwarf galaxies, and we only see a few dozen. Right? So some of these discrepancies may be due to the incomplete sky coverage by current surveys like SDSS.
So it was possible that, in fact, there's a vast number, as you say, thousands of potential dwarf galaxies out there. We don't see thousands. So is it possible that it's these clumps of dark matter that might be surrounding the galaxy, and that's all that's left of these dwarf galaxies?
Absolutely. And one possibility is that you could have nearly dark matter galaxies that have been stripped of their luminous material, or maybe just have a few stars essentially, and that's all you have left. And so those are very difficult to detect optically, and that's why I've been trying to develop alternate methods of hunting for them by analyzing their gravitational effects on the larger spiral galaxy that they're interacting with.
And I guess that was going to be my next question, right? Is that I know that the way that astronomers have been detecting the dark matter further out in the universe is looking at using gravitational lensing to sort of see the distributions of dark matter. Could that technique, I mean, in this case, it was found really close to the Milky Way, but could that technique be used to push a lot further out into the universe and try and maybe see these things surrounding other galaxies? Could we see some around Andromeda, for example?
Oh, absolutely, yeah. So after I worked on the analysis of the Milky Way data, I wanted to apply the method to a case where you had tidally dominant optically visible companions. And a great prototype for that is the Whirlpool Galaxy, or M51, which has a satellite sitting at the tip of its short arm. And we also have data for the atomic hydrogen gas in this galaxy from the Very Large Array. So, you can basically apply the method. This is sort of the proof of principle of the method, because you can apply it to this case and see, did you get the answer right for the mass of the galaxy, for its location, et cetera, et cetera. So, you can apply the method to really any galaxy for which you have data on the gas distribution, and as it turns out, we do quite well for these kind of cases for M51 and other galaxies in the local volume, which have tidally dominant optically visible companions.
Awesome. Well, congratulations on your find. We reported on this, I guess a couple of months back when you first made the announcement, and I think Brian was like, "Well, she's just down the hall from me, so so I think we can get Dr. Chakrabarti on the show. So let's do that." And this is terrific. This is probably one of the first times that we've had a chance for someone to make a discovery and then have that person show up here on the Weekly Space Hangout and discuss the findings. So we really appreciate you giving us the update. And if you make some of those further findings, and as the new surveys come out, by all means, let Brian know, and we'd love to have you back on the show.
I will, absolutely. Thank you so much for having me, Fraser.
Thanks a lot. Take care.
Goodbye.
All right, let's get rolling with the rest. Apparently, other things happened in space, not just dark matter galaxies. So, for starters, of course, the reason that we had to push this show back was because there was a launch of a spacecraft. So why don't we talk a bit about that, Morgan?
Yeah, so this afternoon here in North America, we saw the launch of a Soyuz capsule carrying an astronaut and 2 cosmonauts on their way to the International Space Station. Now, the capsule won't actually dock for a number of hours yet, but when it does, it's going to be carrying a pair of astronauts who will be undertaking a new kind of sort of test in space, and that's to push the boundaries of long-duration space travel. And from the United States is astronaut Scott Kelly, and from Russia is cosmonaut Mikhail Kornienko. And they're both going to be spending a year in space to test the effects of that experience on the human body as well as the human mind. And Scott Kelly offers a particularly interesting opportunity here because he has a twin brother who was also an astronaut, Mark Kelly, who will be staying here on the Earth. But they've been running both physical and mental tests on these astronauts now for a period of time leading up to the launch, and they'll continue to track both of them, one on Earth and one in space, over the course of the next year. And then, again, of course, make a lot of measurements about them when Scott Kelly returns back to the ground. And the goal here is to understand what needs to be done to help humans undertake long space voyages. Because even a year is not really enough time to go anywhere in our solar system. If we're talking about going to Mars, for example, we're talking about a journey that's probably 2 or 3 years in total length, and that's just something we have no experience with yet. And so we need to understand what we have to do to support the astronauts physically, emotionally, psychologically, so that they can function in an optimal way and return to the Earth as healthy as can possibly be.
Now, the internet tells me that Valery Polyakov was the longest space flight that's ever happened, and he was up there for 437 days. And Sergei Avdeyev was there for 379 days, and then a few other people were there for 365 days, and then it kind of goes from there. So this is, a year. This puts them into the top 3 of long-duration space flights. So this is a serious amount of time in space.
Right. Scott Kelly will become the American with the most continuous time in space. Mikhail will not become not reach the top of that list for the Russians. But I think what's unique about this is the focus that is being put on continuous measurement and tracking of their progress. In the past, the Soviets and then the Russians did these things to show that it could be done, but without the sort of strict medical and psychological eye of tracking sort of on a day-to-day basis what the progress of the human body is. And that's what we need. We know it's possible, but the question is, what can we do to mitigate the trouble as much as possible?
Well, and this is it, right, is that we really still, although people have done fairly long-duration space flights, we really just don't know what happens to the human body. And it's like, more specifically, we just don't know, like, what is the time frame. Like, we know it ruins it. We know it tears your muscles apart, it dissolves your bones, it makes your organs funny, it kills your eyesight, it does a whole bunch of really awful things to the human body. Some of which recovers fairly rapidly when you get back to Earth, some of which, we're still uncovering the problems of long-duration spaceflight, not to mention the radiation issues. And so, as we travel, we're either going to need some kind of artificial gravity system, or we're going to have to travel in short enough periods of time where the long-term health issues are minimized, where they don't come back with heart disease and diabetes and who knows what are the problems with us. So by watching him die, as watching his body get torn apart in space as best they can to prevent it, they'll get a sense of, like, what is the danger area, what are the time frames that this is feasible. So it's a really great experiment. I'm really glad they're doing it.
We did a back of the envelope calculation, Fraser, earlier this week, and spending a year on the ISS orbiting the Earth, you will physically put in the miles to go to Mars and back, roughly. You'll actually, just counting the mileage going around the Earth. Of course, you're doing it inside the Earth's radiation, the Van Allen belts, so you're not getting the same rad exposure, but you are putting in the miles.
Yeah, absolutely. So it's a toughie. This is going to be quite an adventure, and when he comes back, he will certainly be tired and need a break. So when do they dock? And David, can people watch this?
NASA TV goes live. NASA TV goes live tonight at 8:45 p.m. Eastern Time. Somewhere past 9 o'clock, I believe they're going to dock. So about 4 more hours. They're on a fast track for orbit docking.
But if you wanted to watch this, what would you do?
NASA TV.
No, but like with the telescope.
Oh, with the telescope, well, you'd have to be in the right part of the Earth. I believe they're docking. It's usually over the ocean they're going to be docking. I know the passes aren't favorable. I know some ham operators are going to try to pick them up going over Europe. One of the dockings a few months ago, actually, they did see them paired up, but it's not favorable for North America, unfortunately, this time.
Right.
I have seen the shuttle dock before. It's kind of cool.
Yeah, well, that's the thing that's really great, right? Is you see the International Space Station go overhead, and then you see this other light following, which is the space shuttle. And if it's even a real favorable pass, you might see them pass by, and then 90 minutes later, you'll see a pass to the south, and they're closer, right?
Yeah.
And eventually
I've seen the shuttle like as a pair going across right, but you got to catch them right before docking, and it has to be when they're illuminated right before sunset or sunrise. So it's a tricky thing to do, but I have seen it before, and I've seen Dragon do the same thing once too.
It's the kind of thing that Thierry Legault would go out and find.
Yeah, he would travel to somewhere in Antarctica to do it though.
Yeah, exactly. All right, well let's move on. Dave, let's talk about the eclipse season.
Yeah, last Friday we had the first eclipse of the year of the 4 eclipses that are happening, 2 solar and 2 lunar, and this was the only total solar eclipse. And I saw I'm still seeing amazing photos a week later in videos coming out. I spent most of that day compiling a huge post on all the photos. It amazed me considering how remote the path of totality for this eclipse was. It went over the North Atlantic, and the only place it made landfall was the Faroe and the Svalbard Islands up in the high Arctic. It amazed me how quickly we were getting all this stuff in. Like, before the eclipse was even over, we were seeing photos of it online. I mean, contrast that back to the 1990s when I was at an internet cafe trying to watch a total solar eclipse, and I got like 1 or 2 very grim stills before the computer crashed, you know, on a dial-up modem trying to watch this thing. So it's amazing to me now how quickly all this stuff. In every eclipse I watch, whether it's online or in person, there's always some new things that people are doing. I've seen the LOFAR array in Europe. They managed to actually get a radio image of the eclipse, which I didn't even think was possible. It took me a while to get approval to use it. I saw the flight.
Did you see this?
Yeah, I saw this, and it took a while for this to really catch fire on the internet, but it was pretty amazing where they actually had a flight of eclipse chasers that went up over the poles and managed to fly their planes into totality, and that was pretty amazing there as well. And you figure how remote that was up there.
Yeah.
This eclipse was unique in that totality ended. It was it was about 13 hours prior to the start of the equinox, and the path of totality ended almost right at the North Pole. So there was a lot of talk about, and I had done some simulations about what it would look like to sit at the North Pole on the vernal equinox and watch this eclipse right on the horizon on the first day that the sun comes up and you would actually see it. So yeah, it was pretty amazing.
I posted that picture on the guy who had taken the picture and taken the video of the eclipse from the stratosphere, and they've actually got a video, and you watch the shadow of the moon pass across the planet as the sun gets darkened by an unbelievable picture and a
yeah, we've seen that.
And everyone
too.
was like, fake. Everyone was like, no, it's fake. And I'm like, no, it's legit. These people actually did this.
I was a few days prior trying to say, you people need to look at this on Twitter. This is too cool. It took a while for that video to really catch on, but we have another eclipse coming up next weekend. See, North America missed out on the solar eclipse unless you lived way out on the east coast of Newfoundland. You got a part of a solar eclipse there last Friday, but we have a total lunar eclipse, one of 2, coming up on April 4th on Easter weekend. This is part of the lunar tetrad that's starting all the hysteria around the blood moon and everything else. And this is going to be a very short total lunar eclipse, and we're actually going to miss it here in Maine, but in a line west of us here, you're going to see this at moonset near sunrise. You're going to actually see a very short, 4 minutes in duration, roughly, give or take a few seconds, total lunar eclipse. This is the shortest lunar eclipse for this century, and you have to go all the way back to the 16th century to find a lunar eclipse that was shorter in duration. The reason being is this Saros cycle of eclipses 132, this is the first total lunar eclipse for that Saros. I wrote a whole explainer post this week on the Saros.
Yeah, there's a thing on Universe Today just about all this. But so then what, who is best equipped to see this upcoming lunar eclipse?
At Hawaii, you're going to have it right straight overhead. You're going to have it right about midnight overhead from the Central Pacific. Over toward like the Asian Far East, they're going to see it in the evening time, which is usually prime time to get out and watch. They're going to see it after sunset. In the Pacific West Coast, where you guys are over there, actually British Columbia, you'll see it very early in the morning. Okay. You get up around an hour or two before sunrise. Like I said, we're not going to see it here from Maine, actually. This is the only one from the lunar tetrad. I'm probably going to watch this one online.
But it's not going to turn that deep red and stay in full eclipse for a long time, right?
Not a long time, no. It's only total for 4 minutes, so it's going to be a very bright eclipse. The northern limb of the moon is going to stay probably pretty bright. But I fully expect to see some awesome photography.
Yeah.
What's really cool, though, when the moon is low on the horizon, if you got sunset and sunrise, and the moon is low on the horizon, you can do a lot of photography with mountains or statues or flags or things in the foreground with the eclipse. When the eclipse is straight overhead, you can't really get that foreground kind of photography. So I fully expect some pretty amazing things to come out of this one.
Oh, that sounds great. And then there's another solar, right?
There's a partial solar, but it's only for South Africa. The eclipses tend to happen in pairs when the moon is near one of its nodes where its orbit intersects the ecliptic. And we're in the middle of one of those seasons right now, and the next season happens in the September-October time frame. So that partial solar is not going to be widely observed. It's down Corey Schmidt way down there toward South Africa.
Right.
He might catch it down there. And then there's another total lunar. All these total lunars, we've been very lucky. They've all been lined up for North America, so they're seeming really common now because every 6 months we're getting a total lunar eclipse for North America.
I remember when there were no lunar eclipses for years.
The next one after this year is 2018 for a total lunar. So we're gonna go into a dry spell again.
Yeah.
And we've only got 2 total solars. The one last month, or this month still. The one in Southeast Asia in 2016 in the springtime, and then is the big ticket event in 2017 is the big total solar eclipse over the U.S. So
do you know roughly how many days we are away now? Some like 900-ish.
We're probably in the 900 range. We're well within 2 years now, so it's that's gonna be interesting. And I listened to the podcast you guys did on the Eddington experiment for the 1919 eclipse. It got me thinking about what stars might be near the 2017 eclipse. Ironically, Regulus is going to be within 1 degree of the eclipsed sun at that time, so I'm kind of wondering if we might be able to find a way to replicate Eddington's experiment during the 2017 eclipse using Regulus, which is a pretty bright star.
Yeah, that'd be great. We can finally prove Einstein right.
That would be good.
Yeah.
All right, let's move on. Brian. You know what? I'm going to take your second one first, which is that the Large Hadron Collider isn't going to disprove the Big Bang. See, now this is all I've been reading on the internet. Is that that and a gigantic asteroid is going to smash into the Earth? So wait a minute. What? Large Hadron Collider is not going to disprove the Big Bang?
Yeah, apparently it's going to disprove the Big Bang and find rainbow gravity and parallel dimensions. And so,
is this where we
apparently they have a lot on their table?
Cosmic age of together oneness as we
dawning of Aquarius.
Into the dawning of the age of Aquarius. Yeah, all right.
That's astrology speak.
Yeah. This actually stems from a paper where. It's very speculative, but there's this work that's looking at something that's called rainbow gravity. It's actually based off of an idea called general locality. So in relativity, we have things like time dilation and length contraction and things like that. And it means that what we consider to be distances or the duration of time varies based upon your point of view. But the one thing that every frame agrees upon is that if an event happens in a specific location, say between 2 particles, everyone agrees that that event happens in that location. In other words, they agree that they're simultaneous. So when 2 points come into contact, everyone agrees with that. General locality is an idea where they may not be that way. It's a way of trying to introduce the kind of quantum fuzziness to relativity. So it's generalizing the idea of what locality means. And one of the consequences is that instead of objects always following the shape of space and time, it depends upon the energy. So it's the momentum of an object that can affect what space-time you might see. And what this means is that light of different energies would follow slightly different paths. So you would get, rainbow gravity. This is something that would not.
Can't say that with a straight face, can you?
It's it's one of these things that it's an interesting idea, but there's a lot of interesting ideas. You know, it's one of those things where you try and come up with this, how do we unify quantum gravity? How do we approach this? And so, you know, Smolin and others have put this idea out. Okay, fine. Try it a little bit. It doesn't quite seem to work, but, you know, you got to try something. You got to do these kind of crazy ideas.
So when you say sort of rainbow gravity, so we're talking about light, like say you've got white light and it's moving through a gravitational well, the differing energies of the photons in the gravity get separated by the gravitational well,
Right.
and so then they literally turn into a rainbow as it comes towards our detectors.
Basically, yeah. I mean, you would see, you know, you have gravitational lensing. This would be like a gravitational prism.
Right. And so, but this so far this has not been demonstrated.
No, there's been no evidence for it, and the work that's basically arguing for the LHC is that because of rainbow gravity and because of parallel dimensions or whatever, you would get micro black holes. It's basically this thing that, well, if we assume this, and if we assume this, and if we assume this, then we'll get micro black holes. And if rainbow gravity is true, then the micro black holes will decay slightly differently than they would with traditional models, and we'll be able to see it. And this will prove rainbow gravity and parallel dimensions and everything else.
Right,
it's
and
a
so I
crazy
guess
idea, but
back to this idea of microscopic black holes, this idea that I guess shortly after the Big Bang there were places of such high density in the early universe that you could have had these primordial black holes be created, right. And that's really the only time that these things could have gotten created, because later on you need stars or whatever the hell it was that made supermassive black holes. But right. Should they be able to create these by smashing particles together, they'll make black holes. You know, you get enough density of matter in a place, you'll make a little black hole, and then it will dissolve again, just as right. Stephen Hawking predicted. So yeah. Hawking will be right. But then you're saying that the flavor, the way these black holes evaporate, right. will help define if this rainbow gravity is true. So now we take this big long journey, hammer the point home. How does this make the Big Bang wrong?
It doesn't. Because people think of one of the consequences of rainbow gravity is that the Big Bang would not have a primordial singularity. It wouldn't begin as a singularity. It would begin as a quantum state or not have a beginning, depending on which variation you're talking about. And people confuse not having an initial point singularity with not having a Big Bang. When we talk in astronomy or cosmology about the Big Bang, what we mean is an early, hot, dense state for which you have the cosmic microwave background and everything else. What got the universe to that state could have been a singularity, could be the after effects of inflation, could be a lot of things right. that are still being discussed. But the early hot dense state is not in debate at all, and none of this will show anything otherwise, even if it happens to be true.
Right, and this is sort of that same correlation between evolution and abiogenesis. Right? So evolution explains how species change over time, but it doesn't explain how the first creature arose, how the right. how DNA first got going, and to right. be honest, not evolution's problem. Evolution is doing just fine. Thank you very much. It explains right. the world that we see, and same thing with the Big Bang. So
right.
So okay. So
we'll discover rainbow gravity during the 2017 eclipse.
Yeah.
That's it. Perfect. We'll see it in Regulus.
There we go.
And that is the moment we will ascend to the higher plane of consciousness.
There we go.
Okay, cool. Well, let's move on. Morgan, this is super cool and right up your alley, which is that NASA has talked about its plans to go and scoop up an asteroid.
Right, so over the last couple of years, NASA has been putting forth this notion they call the asteroid retrieval mission to get an asteroid or a piece of an asteroid, bring it back into orbit about the moon, and then use the SLS and the Orion capsule to send astronauts there to check it out and do some unspecified things once they get there. But they'd kind of been speaking about it in nebulous terms. And they had two basic plans put together, and they hadn't picked until this week between them. And the two ideas were, one, to send a small spacecraft out to a small asteroid, something in the sort of 5 to 10 meter range, and then throw a plastic bag around that asteroid and drag it into lunar orbit. You might have seen sort of a nifty animation that NASA released last year showing how this process might happen. The other idea was to go to a much larger asteroid, go down to the surface, scoop up a boulder that might be 5 to 10 meters in diameter, and bring that boulder back and drop it off in lunar orbit rather than the entire asteroid. And this week, NASA opted to go with that second plan. And some have called that the less ambitious plan. It's the more expensive plan by about $100 million. But NASA's stressing that this is the more flexible and therefore the more reliable plan. Because when you got to, under the original idea of going and scooping up an asteroid wholesale, if you got there and something wasn't right, you're pretty much screwed. Maybe the asteroid was a funny shape and you didn't expect that, or it was bigger than the best models had suggested, or maybe it was a pile of rubble instead of an actual single body, then the whole mission was basically scrapped, and what NASA's positioning as the short-term future of human spaceflight would be over, basically. And they're saying that with this new idea of picking up a boulder instead, they're going to have a lot more flexibility, because a lot of these asteroids that we've gotten a close-up look at, you think about Rosetta at Comet 67P, for example, we see a lot of stuff on the surface. And so you get there, then you decide what you're going to scoop up. And you have a lot more options to keep something from going wrong. But if you're looking at this from a science perspective, I think this reinforces the idea that the asteroid retrieval mission is not about science. It's really being undertaken as something for astronauts to do. Because NASA also put forth 3 asteroid targets that they were considering for this mission. And they'll select one of these 3, they say, in 2019, a year before the unmanned spacecraft blasts off in 2020, for a trip to this asteroid and then a 6-year return trip to the moon, at which point astronauts can get aboard Orion on the SLS and head out to the moon. And 2 of the 3 asteroids that they suggest, asteroid Bennu and asteroid Itokawa, are places that we will have already returned samples from using unmanned missions. Itokawa we've already got a sample of thanks to the Japanese mission Hayabusa, and next year the NASA mission OSIRIS-REx will be launching on a multi-year trip to asteroid Bennu to pick up a piece of its surface and return it to the Earth as well. Only the third of those, asteroid 2008 EV5, is an asteroid that we've never been to before. And in some ways that undermines NASA's suggestion that this is the safer option, because if we were to go to that asteroid, there's no guarantee that we'll find something that we can scoop up in our plastic bag and bring it back to the moon with. But if we go to one of the other 2, places that we're going to be certain have objects that we can pick up, the question is, what are we gaining of scientific value? Because we will already have laboratory samples of both of those bodies on Earth, you know, in one case, more than a decade before this mission even launches, and in the other case, half a decade or even maybe a decade again. And I think that is highlighting the fact that the asteroid retrieval mission is really a question of developing capabilities for the human spaceflight, not for scientific purposes.
Yeah, and so that was something that really kind of made me a little disappointed as well, and I think I'm sort of hearing the same thing in your voice, which was that, you know, I think a lot of the problem where we've gotten to, even in the Space Shuttle and the International Space Station program, is just this trying to be all things to all people and say, no, this is all about science. We are launching people on the space shuttle because of science. When we see the output that's come from the robotic spacecraft, and that is a losing argument every single time. But if the reason you're launching humans into space is to learn how to have humans be in space, then this kind of a mission makes absolute sense. But then go after the safe bet, right? We've seen Itokawa. It looks like a pimply, bouldery place with lots of places to pick up and scoop up and bring those things and take those next steps, right? And so there's like this series of incremental steps. I mean, even what's happening, that's why I'm so excited about what's happening with the astronauts, right? Is that they're going to push the limit of how long a human being has been in space and study it very carefully and watch and try and improve our spaceflight. And then same thing with these other missions. Let's definitely send astronauts to an asteroid. Let's have them pick up a boulder. Let's have them try and live on the asteroid for a little while. Let's try and move an asteroid. Like all these things that there's a checklist, 1,000 items long that we could get cracking on one after the other. But as soon as you say it's better for science, you had me and you lost me.
Yeah, and they're really stressing the technology development benefits of this mission over the science. So we know that they want this as the next step for human spaceflight, but they're also talking about the ability to test advanced electronic or electric propulsion engines on this unmanned capture vehicle, and the ability to test new materials and techniques for the bag that they'll put this material in and things like that. I think NASA sees this truly as a technology and technique development mission more than a science mission. But I think their sort of overarching goal at NASA of promoting science is forcing them to present this as more scientifically valuable than it may ultimately end up being.
Yeah, and I would love them to just take every single penny of potential science that they were thinking they were going to do and give that to a scientist to build a robot probe or a new telescope, right? So if you're going to do a $25 million worth of science, just give that, that's a new observatory.
There was talk earlier this week, Fraser, too, that the SLS launch most likely is going to slip to 2019. That's the first actual test launch, and that's really key to have the rocket to get us there. I mean, they just tested the SLS solid booster out in the desert in Utah last week. That was kind of interesting to watch. But yeah, that doesn't bode well if they're slipping it back already.
Well, but it's entirely anticipated, right? That all space missions,
surprising.
Yeah, all new technology takes longer than you think to build it and test it and have it be safe and all that.
It's making the SpaceX's Falcon 9 Heavy look a little better because they should have their first test launch either this year or next year.
Yeah, and I think we've in previous episodes of This Week in Musk, we've definitely talked about that, about how the SLS is now in a race with Elon Musk to deliver a heavy launch vehicle, not to mention what Arianespace is doing, not to mention the new cosmodrome that the Russians are building in Siberia, and the Chinese are planning a new heavy launch vehicle. So 10 years ago, there weren't a lot of heavy launch options, but now they're coming on fast and furious.
I don't think people realized when Orion launched last year that wasn't the rocket it's ultimately going to go on. That's what we had to put it on, basically. So.
Yeah. So what do you think, Morgan? Do you think this is going to happen?
It's difficult to say, I think. I think there's a lot of institutional momentum at NASA right now behind this. There's the feeling that they've kind of danced in a lot of directions for a long time and that they need to commit to something even if it's not maybe the perfect choice. And I think that's a reasonable decision to make. But every year that every year the SLS slips is every year that the ARM mission slips, puts it in much more risky political territory. We're already talking about the astronauts getting to this asteroid not during this presidential administration and not during the next presidential administration, even if that one lasts for 8 years, but at least for the one after that. And that offers a tremendous number of opportunities for this mission to be cut or pared down or refocused, and all of those things are just going to lead to longer delays. And so the faster that they can get this done, the more likely it'll be to happen. And if cutting out science achieves getting it done faster, then I think ultimately scientists and engineers and human spaceflight proponents will end up ahead.
Yeah. That's and if that's the delay, right? You can imagine the second generation of colonists has already arrived at Mars from SpaceX, right? That they'll be, when you think like whatever 16 years, 12 years down the road, that is well within Elon Musk's plans to start sending spacecraft to Mars. So. Cool. All right. Well, let's move on. Brian, let's talk about darker dark matter.
Okay, this is an interesting study. There was a research study of 72 colliding galaxy clusters. And so you might be familiar with dark matter. One of the evidence of dark matter is what's known as the bullet cluster, where you've got these clusters of galaxies colliding, and the dark matter distribution is different from the regular matter distribution. And one of the ways, by seeing that, that's one of the evidences for dark matter. Well, this new work looked at 72 different ones, and the interesting thing about that is that they're not just kind of face on, they're in all different directions, both towards us and away from us, and as well as side to side. And they did two things. One is they mapped the distribution of dark matter from weak gravitational lensing of background light, and they compared that with the distribution of matter to look at basically how strongly is the dark matter presence there. And they confirmed the existence of dark matter to 7.6 sigma, which is, if I remember it correctly, it's like 1 minus 3 times 10 to the 14th in terms of the odds of it being a fake. So it's about as certain as you're going to get. So when you look at these images of dark matter, that is absolutely an image of dark matter. But the other interesting thing that's, for astronomy, since we already have dark matter, looking at how these interact, because when you have galaxies that are colliding, the stars just kind of pass by each other because they're not really interacting. The gas can, collide and slow down and have star formation. But the real question is, when you have these galaxies going, their dark matter, what happens to it? Because dark matter is diffuse. And so if there's a cross-section, if there's a way to interact, if dark matter interacts by itself, then it would collide and kind of stop. It would, interact in that way. If it doesn't interact very strongly with itself, then it would pass through. And so by looking at all of these distributions, what they found was that not only does dark matter not interact strongly with regular matter, it doesn't interact strongly with itself. And so it has a fairly small cross-section for interaction. And the interesting thing is that, if you look at related ones where they're talking about, gamma rays possibly coming off of dark matter colliding, this eliminates some of those. And it eliminates some of the possibilities for models beyond the standard model.
Now, when you say it doesn't interact much, does it interact at all?
Well, to the limits of their observation, it doesn't.
Right.
And so, based on these observations, they were able to put an upper limit. And I think that the upper limit at 96 percentile is about the level of weak neutron scattering, if I remember correctly.
Right, and so like when physicists are talking about the cross-section, what they really mean is essentially, are the particles so big that they go bonk? Right.
How likely, when they come together, how likely are they to interact? Because it's a quantum thing, so it's statistical. Right. But yeah, you can find an effective cross-section, and it's fairly small for dark matter.
But it can't be zero, right?
Well,
if it was zero and there was gravitational influence, then wouldn't all the dark matter pile up into one little spot all on top of one another?
That is the understanding that we would have, yes. That we think there is a cross-section, but now what we know is that cross-section is small. And it's smaller than what we've typically thought. There you go. Oh.
Yeah, okay, so let's move on then. Let's take a couple of questions from the audience. So, let's see. So, Nancy Graziano asks, would the detection of gravitational waves be a stepping stone towards possibly validating rainbow gravity?
No.
Okay.
Gravitational waves, any detection of gravitational waves would be so weak that it wouldn't confirm it.
Well, after that short answer, I'm going to give Nancy another one then. So, Brian, does this reinforce the thought that dark matter may be a flavor of WIMPs, the weakly interactive massless particles?
Yeah, the WIMPs are still, some type of supersymmetric WIMPs are still considered the leading candidate for dark matter.
Right. And I think that's the thing, right? That the bullet cluster, what the bullet cluster showed us is two galaxies crashing together the gas piling up, turning into new stars, the stars passing by each other, and the dark matter passing by each other, and you actually see now the galaxy clusters have sifted out the gas from the dark matter and the stars, and you can literally see dark matter over there, but not dark matter there, and dark matter over there. So it's just as opposed to if it was gravity acting differently at long distances, you wouldn't necessarily see that stripping. So
Right. We've thrown out any modified gravity. There isn't anything that agrees with any of the observations at this point.
Andrew Planet asks, are you people officially organizing anything for the 2017 total eclipse?
I'm definitely going to be there.
Yeah,
I don't
me
know
too.
where. Out west, probably. That's your better chances of a clear sky.
I only have to drive a few miles or a few hours to get into the path. So at minimum, I will be making that drive.
I'm thinking Eastern Oregon is what I will probably try to get to.
Yeah, that's probably a pretty big bet.
Fairly clear, close enough to me in British Columbia, so I'm looking at probably 10, 12 hours to get there, though.
And we have another one crossing the U.S. the opposite direction in 2024. So if you stay right around Carbondale, Illinois, you'll see 2 total solar eclipses in the span of 7 years.
Yep. The second one goes right through Rochester.
Yeah, that second
Which
one
means
in
we'll see
2024.
clouds, it'll go dark, and then we'll see clouds again.
That second one in 2024 passes over my hometown of Presque Isle, Maine, so that's probably where I'll be.
Okay, so we've got a couple of minutes left. I want to bring in some questions from the WSH crew, the Weekly Space Hangout crew. This is, of course, the Google Plus community where they talk about the Weekly Space Hangout, and we got a bunch of sort of stories that have been posted. One comes from Nancy Graziano, and this is that the mapping of Pluto begins today, but that was actually about 6 days ago, what the today was. So, Morgan, what's going on with Pluto?
Yeah, so right now in one of the cameras of New Horizons, Pluto appears to be 3 or 3.5 pixels across, which gives it an area of about 9 pixels in size. That's still much smaller than what we can see in, say, Hubble. It'll take about another 2 months before New Horizons gets close enough to Pluto for it to get more detail than Hubble has. But there's enough detail right now to start making out dark spots and light spots. And what they're going to be doing over the course of the next few months is tracking those spots and watching them resolve into smaller and smaller, more distinct features. And unlike pretty much any previous large-scale astronomical discovery, say Voyager's visit to Neptune or Uranus, the New Horizons team is offering the public an opportunity to name pretty much all of the features on the surface of Pluto. And so as features sort of become distinct and detected, they'll become available for the public to suggest and presumably eventually vote on the names for.
That's pretty cool. As the resolution gets better and the features become resolved, they can start naming them. I love it. And I guess kudos to Alan Stern, who of course is the primary investigator for New Horizons and is all about both Pluto's planethood and naming features. So
New Horizons will see the most distant solar eclipse ever when it flies through Pluto's shadow too. That's going to be kind of cool.
Oh, neat. Okay.
They're actually doing an experiment in relation to that.
So this next story comes from Jim Meeker, and this is that NASA has reformatted the memory of the longest-running Mars rover.
Right, so you might remember a few months ago, Opportunity was sort of randomly shutting off, basically crashing in the middle of its observations. And to sort of put that problem on hold, what they had done was stop using the memory on board, because there were basically bad chunks of memory that when the spacecraft computer encountered them was causing it to freak out and restart. And so they were every night transmitting all of the data from that day, including Opportunity's position, orientation, vital information back to Earth, and then the next morning transmitting it all back to Opportunity and basically restarting it from scratch. And they finally developed a patch that's going to allow the computer to navigate around those bad segments of memory and use only the good ones. And that leaves about 6/7 of its original memory intact, and they're confident that they'll be able to operate opportunity pretty much unimpeded without having to go through this sort of annoying beam up, beam down process that they've been doing since late last year.
What a terrifying process, though, to try and remap the memory of your rover that's on another planet, and you have to reboot it multiple times, and you can't just go and unplug cards if you need to until Mark Watney can come over and help out.
Opportunity is busy terraforming Mars. If you saw today's XKCD cartoon.
Yeah.
That's awesome. It just completed its marathon. So, congratulations, the slowest marathon ever, but the fastest on another planet.
I want a T-shirt that says that I'm still faster.
I'm still faster than Opportunity. Cool. All right. So we should probably wrap this up. So let's give people a chance to explain where we can find out more. Brian, where do we find out more?
You can find me on my website. It's one universe at a time, briankoberlein.com. You can find me on Twitter at briankoberlein. If you go to patreon.com/briankoberlein, you can contribute to my slush fund, I guess.
Your podcasting production fund.
Yeah. So,
how's that going? You've done
podcast,
another podcast, right? You've got, what, 2 out now? 3?
2 of them out. The third one comes out tomorrow morning.
Fantastic. That's terrific. Dave, where do we see more?
See, I was active this week on Astro Guys, Universe Today, and Listosaur, and I have my own science fiction author page over on Amazon where I'm self-publishing stories and science fiction, and I have a new article today on Universe Today about a Guide to Space post about what drives the solar cycle and things we still don't understand about the sun.
All right, Morgan, where do we find out more?
All right, well, before I plug me, Pamela Gay asked me to plug the CosmoQuest Hangout-a-thon, which is now less than 1 month away. That'll be starting in the morning of April 25th and extending through April 26th. So you can see all of the CosmoQuest people over there, as well as many of your favorite space personalities from around the internet. So keep an eye out for more information about that as the date approaches.
Well, maybe we can do another Fraser and Morgan astronomy cast. I think it'll be fun to recreate that.
Yeah, I think we can come up with something that you and Pamela haven't covered in all of space and science.
Yeah.
There's got to be one thing left somewhere, possibly. But you can find me right after the show over at the Google Plus Space Community, where I'll answer any questions that we didn't get a chance to get to during the show. Just go to plus.google.com, click on Communities, and find Space. You can find me at Morgan Rehnberg on Twitter for anything you have elseways in the week.
That's great. And of course, I am Fraser Cain, publisher of Universe Today. You can find me FKain on Twitter. I'm on Google Plus, on YouTube. We're still working our way to 50,000 YouTube subscribers. So if you're watching this video right now, click subscribe, and then that way you'll get more notifications about when we're recording and all the other videos. We had some really fun ones this week. We talked about whether the universe is finite or infinite. Can the Death Star destroy the Earth? And a bunch of other topics. So it was a lot of fun. Well, hey, thanks, guys, for joining me this week, and thanks to Chakrabarti for joining us at the beginning. As always, if you want more special guests to join us on the Weekly Space Hangout, the way to do that is to join the WSH crew. That's, of course, that Google Plus community, and they are hard at work finding guests for the Weekly Space Hangout, and we are glad to get their help. So that's the place to go and talk to them and help them organize some new guests for the show. We will see you all next week.